Here we have a couple of sample problems. In our first problem, we have 275 grams of propane, C3H8, burning in a barbecue, and we're asked to find the volume at STP of oxygen required for the reaction. Would we likely do this at STP? No, we'd probably do it at SATP if anything, but it's a combustion reaction. It can be weird to try and measure the temperature anyhow. So it's fine for measuring it at STP. First thing we need to do, this is a combustion reaction, which means we're going to have propane reacting with oxygen, producing carbon dioxide and water vapor. This is where it becomes really important to have all of your states. And the reason that's really important is we need to know if we can do gas calculations or not. Well, oxygen here is a gas, so we can do gas calculations for this. Our next step is going to be to list out our knowns. The known mass is given to us, 275 grams of propane. The molar mass is not given to us directly, but we have our periodic table. We know that carbon has a molar mass of 12 1/100th of a gram per mole, and we know that hydrogen has a molar mass of 1 1/100th of a gram per mole. Next thing, we're going to write out our unknowns. We want to find a volume of oxygen, and we're being asked to find volume in liters. So we don't want to use molar mass for our oxygen. We want to use molar volume. Because this is at STP, we know the molar volume is 22.4 liters per mole. That means we can just take a quick shortcut. We're going to switch out our molar mass and use molar volume instead. Last of all, we need our ratio. In this balanced chemical equation, we have a ratio of 5 oxygens for every 1 propane. Now we can start doing some calculations. I know that I'm going to want to start with my mass over here and work my way around till I get liters. So first thing I'm going to put in is my mass, then my molar mass, then my ratio, then my molar volume, and that will give me the answer. So when I do these, I just make sure that I arrange everything so that the units cancel out with each other. So I'm going to flip the molar mass upside down, so I put moles on the top. Remember as well, write out the chemical being involved because we're going to want to cancel that when we put in our ratio. So I have moles on top for my molar mass. I cancel out the propanes and replace it with oxygen. So by the second step, I've calculated the moles of oxygen. And then I'm going to want to cancel out this mole here with this mole here, and that will leave me liters in the end. And I should find that I get 698 liters of oxygen. In my second sample problem, I'm given a bit of information about ammonia. It's widely used as a fertilizer and is produced from the reaction of nitrogen and hydrogen. Aha! Right there, I've been told what the reaction is. So I can write down my balanced chemical equation. Nitrogen and hydrogen are reacting to form ammonia. In order to balance it out, I need 1 nitrogen, 3 hydrogen molecules, because remember, nitrogen and hydrogen are N2 and H2 respectively, and I need 2 moles of ammonia produced. Okay, moving on. What volume of ammonia at 250 kPa and 80 degrees Celsius can be obtained from the complete reaction of 7.8 kilograms of hydrogen? Okay, so this time I'm not told it's at STP or SATP, so I can't use my molar volumes. Instead, I'm going to have to use some ideal gas law. Now you could do this stoichiometry to solve for the number of moles, but then do ideal gas law afterwards, but it's actually quicker if you do the calculations using unit canceling, your ideal gas constant, and as well, if you're going on into Chemistry 30, that builds an important skill, because in Chem 30 you're not given formulas on the diploma at the end of the year. So you need to be able to do some unit canceling. First thing I'm going to do is write down my knowns for hydrogen gas. We are told that 7.5 kilograms of hydrogen react. So I can write that down. And remember, hydrogen is H2. So it's not 1.01 grams per mole, it's 2.02 grams per mole because there's 2 hydrogen atoms. Then I'm going to write out my unknowns. So for my ammonia, I know that the volume is what I want in the end. The temperature I'm going to convert to Kelvin. So I'm told it's 80 degrees Celsius. That means it's going to be 353 and 1500ths Kelvin. I have 45 kilopascals and my R stays the same. It always does, 8.314 kPa liters over moles Kelvin. Finally, I also need my ratio. So the ratio in this is that I have 2 moles of ammonia produced for every 3 moles of hydrogen reacted. So from there, I can just do the exact same thing as I did in the last question. It's going to take a little bit more work because I have more stuff to cancel out, but works basically the same way. I start with my mass. I'm going to cancel out using the molar mass, cancel out using the ratio, and then I'm just going to work up this list. So I'm going to put in my R next so that I cancel out the moles. Then I just have to cancel out kPa and Kelvin, and that will leave me with liters in the end. And it will look just like this. So I start with 7.5 kilograms of H2. Remember, write the chemicals formula in. I'm going to cancel out the grams so that I have moles. So I'm going to flip hydrogen's molar mass upside down so grams and grams cancel out. Then I'm going to use the ratio to cancel out the H2s, and then I can move on to my values for the ammonia. I can use the ideal gas constant to cancel out moles. I don't need to flip this one because I already have moles on the bottom of the ideal gas constant and moles are on the top of my molar mass. And then from there, I just need to cancel out kilopascals and Kelvin. Kelvin's going to go up on top of a fraction because I have Kelvin on the bottom of my ideal gas constant, and then kilopascals goes on the bottom because it's on the top in the other value. So that will cancel everything out, and we end up with an answer of 16 kiloliters of ammonia. Okay, why 16? Because we have 2 significant digits in the kilograms, and we actually did have 2 significant digits way back in the Kelvin as well. The other thing is this is kiloliters. I left this in kiloliters because I started with kilograms, and it's actually a little bit easier maybe to think of 16 kiloliters than 16,000 liters. That number could seem overwhelming to people. You could do this in liters though just as well. You would just have to use scientific notation to make sure you have the correct number of significant digits. If you wanted to do this calculation and get liters in the end, all you would do is convert the first kilograms into grams before you start your calculations.